learners, welcome to this fourth session of Chemical Equilibrium. Myself, Professor Kamalika Banerjee of the School of Sciences, Indira Gandhi National Open University, welcome you all. I hope you could understand the previous sessions of Chemical Equilibrium, but still feel free to post your queries to my email Kamalika KAMALIKA @ignou.ac.in, and also we have a WEAS blog in the School of Sciences website, School of Sciences page in the IGNOU website. So, you can post your queries there also. Now, as we did in the previous sessions, we started from the reversible and irreversible reactions, the dynamic chemical equilibrium, then the reaction quotient, equilibrium constant, and the relation between them. And then in the previous sessions we came up with the Kp, Kx, Kc, that is the equilibrium constant in terms of pressure, mole fraction and concentration, and we also saw how they can be converted from one to the other given certain parameters, and also you must be able to do problems related to those, which I have discussed some of them, and you can do more of them from other books also, good books of physical chemistry of undergraduate standard. So, now basically I hope till now you have understood that this equilibrium, this chemical equilibrium, it involves a dynamic equilibrium, and also the equilibrium composition, the chemical composition at equilibrium is the same whether you arrive from the reactant side or from the product side. And also you must be following that you can express the chemical equilibrium constant in terms of pressure, mole fraction or concentration, anything. Now, in this session, let us study the applications of equilibrium studies, how we can apply them in real life situations. You know, for Kc, we have to find out the Kc with the help of the equilibrium concentrations of all the terms that are there, all the concentrations that are there in the equilibrium constant expression. So, whenever you are doing this, how should you do? You must follow a method, like when you are I will show you this how to do this calculations, this methodical way. You see this with the help of this example. Dinitrogen tetroxide N2O4, when heated, it dissociates to form red brown NO2 gas. So, here this is a photo of this formation of brown NO2 in boiling water, and next you see the opposite, just as I told you before, that you must imagine the reversible reactions, they can happen from any direction, from left to right, right to left, reactant to product, product to reactant. We have, by this time you must have got this concept of the reversibility. So, here is the left to right, that is reactant to product, what happens, and next here this photo you see, if in this ice cold container the conditions have changed, the ice cold container, here you are getting the N2O4, and that the color is becoming lighter hence. Now, if we are taking 2 mole of N2O4 in a 5 liter flask and heat it to 407 Kelvin, then immediately a dark red brown color appears. So, we understand that yes, this NO2 is formed. Now, if you are measuring the intensity of color we can see that the concentration of NO2 at equilibrium is 0.525 mole per liter. Now, to use this information to calculate the equilibrium constant, first you should write the balanced equation, then you write the Kc, the term, that is the product raised to the power of the stoichiometric coefficient in the numerator, and in the denominator the reactant raised to the power of its stoichiometric coefficient. Next, you have to consider this chart. Okay? You write down the initial concentration, what is that, 0.4, and change as reaction occurs, those are not given, so those will be blank. And next, the equilibrium concentration, what is given, the NO2 equilibrium concentration is given. So, this is the way you start your calculation in a tabular form. Next, you see, you have to assume certain things to go on with the calculation. So, you take the change in concentration of one substance to be x. Okay? So, let us take the change in concentration of NO2 as x. So, what are the unknown now? See, the initial concentration of NO2 will also be 0, that is also known. Now, change as reaction of N2O4 is not known and equilibrium concentration of N2O4 is not known. So, how do you that? How do you do that? We see what will be the change in the concentration of N2O4. What will be the changes in the concentration of N2O4? If the concentration of NO2 is assumed as x, what should it be? It should be half of it, isn't it? Look at the reversible reaction. From 1 mole of N2O4, twice NO2 is formed. So, the change will be minus half of x. Okay. So, now we put that value. The change in concentration of N2O4 will be negative because it is decreasing. Formation of NO2 is taking place, so it will be positive. So, now the equilibrium concentration will be then 0.4 minus half x for N2O4, and here we were given the equilibrium concentration of NO2 as 0.525. So, that is nothing but the initial concentration of NO2 plus the change, that is x. Okay? So, you must enter these in the chart. Now, next what you have to do? The table is becoming this same, but you are writing it in a cleaner way. Okay? So, next what you do? Simplest possible equation you must use to solve x. So, you see, for here 0.525 equal to 0 plus x. So, x can be taken as 0.525, isn't it? So, Kc, if you put there the values of the equilibrium concentration of Kc, on the numerator you put 0.525, and here in this denominator the equilibrium concentration of N2O4 will be 0.4 minus half of nothing else but 0.525, which is x. So, we put those values 0.138 for N2O4 and we get the value of Kc as 2 at 407 Kelvin, the temperature. So, you see it is very easy if you write in tabular form and do these calculations. Next, we are going for another example where you will see that the equilibrium constant is so high, greater than 1, that the concentration of the product at equilibrium is much larger than the concentration of the reactant. You consider this gas phase reaction, hydrogen plus iodine gives hydrogen iodide. So, initial concentration of each, if you take as 0.0175 and heat it to 425, what happens? The concentration of hydrogen and iodine will decrease while Hi will increase according to this equation, reversible equation, and at equilibrium concentration it will be the hydrogen iodide is 0.0276 mole per liter. So, can we find out the Kc? Yes. Again, for this you first write down the balanced equation, then write down Kc, which is equal to product raised to the power of stoichiometric coefficients divided by the reactants to the power of the stoichiometric coefficients. Next, you again put the table. Okay. So, here in this table you see initial concentration of hydrogen, iodine, Hi, then change as it occurs. If you take X to be the change of Hi, then the hydrogen iodine will be minus half of X, half of Hi they are decreasing and minus because they are decreasing. So, the equilibrium concentration, you know what is it, which is the value given, and you take a hydrogen and iodine, they are given as 0.0175. So, you decrease minus half X from them, and Hi is equal to 0.0276, which is 0 plus X. So, you substitute these values in the Kc term for the equilibrium concentration. You can do easily because you are knowing X is the simplest equation you see for Hi, X becomes 0.0276. So, you take this value of X and you substitute in the concentration of hydrogen and iodine, you minus half of that 0.0276 and you get the value of Kc. You see, how can we check whether the answer is correct? You are getting the value is much greater than 1 and it should be so, because the more products than reactants when equilibrium is reached, and it is given that 0.0276 larger than those of the reactants. Okay. So, similar way, if you do other problems where you are given these table, you see selected equilibrium constants are given for different equations, and you may be given any similar problem. You may be given Kc or Kp or any initial concentration or anything, and you may be able to calculate Kc or Kp, or you are given mole fraction of anything, you are able to calculate, you are able to calculate from the partial pressure. So, any such problems using these values of Kc and Kp and the given conditions of the problem, you can find the unknown value which is asked for. Okay. So, next we come to the significance of the value of the equilibrium constant. We have already learnt it that the reaction quotient and the equilibrium constant, both of them has relation, recapitulate those, and it is very important that equilibrium constant tells us how far the reaction has proceeded when the equilibrium has been achieved. So, what does it help us to do? It helps us to calculate how much product will be there at equilibrium condition. So, let us take the first case, Kc, when it is much greater than 1, then it is strongly product favored. So, the concentration of products are much greater than the concentration of reactants under equilibrium. This sign means greater than. So, when the equilibrium is reached, the reaction almost goes into completion. If reaction is slow, this could take a lot of time. Whenever the value of Kc is more, then the products are strongly favored over reactants. You see this example, nitric oxide with ozone, the way ozone is destroyed in the stratosphere. You see the value is 6 into 10 to the power 34. So, how easily the ozone gets depleted in the stratosphere. This very large value of Kc shows that in the flask we will get only NO2 and O2 if we do such reaction. For practical purposes, this reaction goes to completion, and it is not necessary that we use equilibrium constant to calculate the quantities of products that would be obtained. Now, if you use the opposite direction symbol, then it means much less than, which is there in case 2. If Kc is much less than 1, reaction is strongly reactant favored, and the concentrations of the reactants are greater than the concentration of products under equilibrium conditions. On the other hand, an extremely small Kc means that if equilibrium is achieved, then very little of the reactants have been transformed into products. Okay. So, you see this example, oxygen to ozone. The equilibrium constant you can write as this, where the product to the power of stoichiometric coefficient is in the numerator, and in the denominator the reactant to the power stoichiometric coefficient. So, the concentration of ozone is so less than the concentration of oxygen raised to their respective stoichiometric coefficients. So, that if oxygen is placed in a flask at 25 degrees centigrade, very little ozone will be found when equilibrium is achieved. So, no reaction almost we can say, NR we say. Next is the case 3, where Kc is almost equal to 1. Here the equilibrium mixture contains significant concentrations of both reactants and products, and here you do need calculations to determine equilibrium concentrations. So, we can find out from the equilibrium constant and calculate how far a reaction proceeds towards product, which is not required for cases 1 and 2, where it is Kc is much greater than 1 or Kc is much less than 1. So, this reaction of dissociation of dinitrogen tetroxide has neither a very large nor a very small equilibrium constant. Okay. So, the product NO2 on the top and N2O4 in the denominator is this, and they are the same, they are same actually. So, NO2 to the power 2 is equal to N2O4 at 391 Kelvin. So, if you put both the values as 1 mole per liter, then Kc will be 1. So, can you say if the what would happen to the value of Kc if concentrations would be much smaller? See, you can verify this with this equation 4 reaction. Let us take the value of the equilibrium concentration of NO2 to be 0.01 instead of 1, and N2O4 then must be the square of that, which is equal to 0.301. So, even though Kc is 1, the concentration of the substance can be much larger than the concentration of the other. This happens because there is a squared term in the numerator of the equilibrium concentration and a term to a different power in the denominator. So, you see, whenever the exponents of the numerator is not the same as the total of the exponents of the denominator, you cannot say which concentration will be more, that of the reactants or the product, unless and until you do a calculation. So, when Kc is almost 1, you have to do calculation to find out the concentrations of either the reactants or the products. Now, if the total of the exponents is the same, then if Kc is much greater than 1, the products predominate over the reactants, and if Kc is much less than 1, reactants predominate over products. So, we have done this equation of dissociation of hydrogen iodide, which falls under this category, much less than 1. So, a question now is very pertinent to ask, that are reactant favored systems in which small quantities of products form are important? Yes, they are. You see in table 1, which we have done before, table 1, there you will find that there are many acid base reactions which have the Kc much less than 1. You see acetic acid, carbonic acid much less than 1. So, they are important. For acetic acid, you see vinegar, the Kc is 1.8 into 10 to the power minus 5. It is so small. The acetate ions and hydronium ions concentrations are very less, much small than the acetic acid molecules. So, it is a weak acid. So, whenever you have the equilibrium reactions for these sort of acids, we have the same form, that is the hydrogen ion concentration into anion by the acid, that is the product on the numerator, and the denominator has the reactants. The anion may be HCO minus, CH3CO minus or HCO3 minus, and acids will be HCOH, CH3COH or carbonic acid. So, the formic acid is stronger, it has a larger Kc values than acetic acid, and of the 3 acids, carbonic acid is the weakest. So, from these you can quantitatively compare the extent to which the reaction is product favored. If the forward reaction has a large tendency to occur, then the reverse reaction has little tendency. So, from table 1 we can see the combustion of hydrogen to form water vapor has an enormous equilibrium constant, 10 to the power 81. So, it goes to completion, we can say. The reverse reaction, decomposition of water to its element, is strongly reactant favored and a very small Kc to the power 10 to the power minus 82. So, using these equilibrium constant, you can predict quantitatively the direction of the reaction. Like if we start with NO2 and N2O4, what will be the equilibrium? So, here again the reaction quotient, the mathematical form which we discussed before, you have to see what is the value of that. Suppose for this equation we get the reaction quotient to the power 10 to the power 2, the Qc. If it is equal to Kc, the concentration will not change. If Qc is less than Kc, then the concentration of products are not as large as they would be at equilibrium, the forward reaction will occur. If Qc is greater than Kc, then much product is already formed. Now, the reverse reaction will proceed until the equilibrium is achieved. So, predicting the direction of reaction is also important, and various problems have been discussed before also, and you can also do whenever you calculate Qc. If you find the value less than Kc, then forward reaction will occur. If it is greater than Kc, reverse reaction will occur, and that way I think we have completed an enormous chunk of chemical equilibrium in this session, discussions on chemical equilibrium, and in the next session maybe we will continue with the Le Chatelier's principle, and we can also say that till now we have, in this session particularly, we have gone into the basic problems related to equilibrium constant and how to calculate concentrations, the equilibrium concentrations through various methods. So, students, learners, thank you.